Welcome to this talk, Enhancing Unsupervised Speech Recognition with Diffusion GANs. My name is Xianzhao Wu from NVIDIA, Japan. In this talk, I'm going to talk about 4 parts. The first is background. I will introduce unsupervised ASR with pretrained Wave-to-Vec models. The second part is a diffusion GAN, which leverages diffusion process to enhance the adversarial training process of GANs. We would like to combine these 2 parts together and propose a novel diffusion GAN enhanced Wave-to-Vec unsupervised ASR model. We will introduce architecture, loss functions, and our major contributions, and then introduce experiments and conclusion. The first background is about unsupervised ASR model proposed 2 years ago in NeurIPS. Initially, the idea is to reuse a pretrained Wave-to-Vec model and use a pair of unlabeled speech audio and unlabeled text, where there is no correspondence relationship between these 2 pairs. So basically, we have 7 steps in training an unsupervised ASR model. The first one is like use the Wave-to-Vec model to obtain a dense representation of the waves, and then do some k-means clustering, trying to combine nearby frames together so that the segment can correspond to an independent phoneme. And we train a generator, a neural generator, to generate a phoneme for each segment. And the generated phoneme sequence will be sent to a discriminator to compare with the pseudo reference text sequence here. And we ask the discriminator to check whether it's a real or fake textual sequence. So basically, this is a use of pre-trained Wave-to-Vec model and adversarial process trying to align the hidden distribution between the audio and the text phoneme sequence. You know, when we use a GAN for training, it suffers from several shortages. The first one is unstable training. The second one is about the mode collapse problem. And to deal with these 2 problems, the diffusion GAN was proposed last year, which has 3 major steps to overcome the shortages of traditional GANs. The first one is introducing of adversarial diffusion process. The second is a diffusion timestamp dependent discriminator. The third is a generator. So basically, we have a golden reference image, and we have a generated image. We do some diffusion process with different timestamps and compare these pairs, the real and the generated images, using a timestamp dependent discriminator, so that we can have rich information that can be sent to the generator to build a more robust generator for our inference. So the major difference is the change of the discriminator from a traditional discriminator to a time-step dependent discriminator, so that we are trying to do data augmentation to the adversarial training. And then comes to our major proposal, diffusion GAN enhanced Wave-to-Vec model. In the model, there are major 3 parts. The first one is processing of unlabeled audio here, which is quite similar with the traditional Wave-to-Vec unsupervised ASR. The second part is, as we know, is unlabeled text processing. So here we have 3 major differences. The first one is that we share the number of segments from the audio part when we sample the textual sequence as the pseudo reference. The second is that instead of random select unlabeled text, we pretrain a phoneme-based BERT model and use this BERT model to sample a given line's textual sequence as a pseudo reference. These two parts, the generated sequence and the pseudo text sequence, will be sent to the timestamp dependent discriminator, which is the third part, a diffusion forward process, so that this a list of discriminators can collect a signal, do the true-false classification, and give a feedback to the generator so that we can train a more robust generator for our final inference. So there are several losses, change of losses, as we said before. The major change is that we are using a timestamp dependent discriminator now. So we have a generator loss, we have a discriminator loss, and also we have a min-max process here. The major contributions include several parts. The first is introducing of a diffusion process so that I can deal with unstable training in using traditional GANs into unsupervised ASR. The second is to keeping the inference latency to be similar with traditional GANs. And we have achieved a better result so that we can combine the GAN architecture and the unsupervised ASR model with diffusion process to obtain a better unsupervised ASR model. So the major result here is that we have several experiments. The first one is on unsupervised configuration for library speech dataset. Under this dataset, we have a significant relative improvement of from 5% to 11.7%. So finally, on the test other dataset, we achieve a WER of 5.6, which is better than state-of-the-art and unsupervised configuration. Also, with a small-scale timid dataset, we can achieve 2.7 to 3.5% relative improvement of phoneme error rate. So to conclude this work, so we have a way to introduce diffusion architecture to unsupervised ASR. We introduce the diffusion enhanced adversarial training, which can give us a stable training and same inference latency because we are not changing the generator part, and also a better result. The future direction will be include open vocabulary and to deal with more Asian languages. Thank you for your listening.